Hi everyone. As you can tell, I am not here today. I have a sick baby at home, so I am at home taking care of him. But we are going to start 6.4. Just so you know, I'm going to go through these examples pretty quickly, so please make sure that you are pausing to take the appropriate notes, and you'll complete your assignment over these examples after you are finished watching and taking your notes. So as you can see, this is over exponential growth and decay. We'll start by identifying exponential growth and decay functions. Interpret and rewrite exponential growth and decay functions. We might get to that today, I'm not sure. So the first formula that we need to be familiar with is the exponential growth formula, which is it's when a quantity increases by the same factor over equal intervals of time. So that's important that it's over equal intervals of time. And the formula is listed right here, where it's y equals a times 1 plus r raised to the t power. A has to be greater than 0, and r has to be greater than 0. So down here below, it breaks down what everything is. Y is your final amount, a is your initial amount, r is your rate of growth in decimal form. That's important that it needs to be in decimal form. T is time, and then the quantity 1 plus r is what we call our growth factor. So that's what we're increasing by over a set or over an equal interval of time. So example 1 says the inaugural attendance of an annual music festival is 150,000. The attendance Y increases by 8% each year. We're going to write an exponential growth function that represents the attendance after t years. So it tells us that we're writing a growth function, so we can start by writing a1 plus r raised to the t, and we need to know what all of these variables are. We need to know a and r. So a is going to be 150,000, and 8%, we need to write that in decimal form. So r is going to be 0.08, and now we can write our equation. So a is 150,000, r is 0.08. It's all raised to the t. Notice that they switched out the variable x for t, so that it acts in place of x. And since we're always talking about time with exponential growth and decay, that's why we use t instead of x. So the final step is to add these two together. And that is our exponential growth function. Then part B says how many will attend the festival in the 5th year. So that means that t is 5, since t represents since t represents years. So plugging that in. And what we get, if you plug that into your calculator, is about 204,073. And that's approximate. So since it's the people, we're going to round to the nearest whole number. What you round to depends on the context. So if we're talking about a value that could only be expressed as a whole number, then you should write a whole number because you can't have a part of a person. Next, exponential decay. So very similar formula, except we are subtracting our rate. Okay, so the difference between decay and growth is that they're almost exactly the same. Notice that this is 1 plus r, and this one is 1 minus r. Y still is the final amount, a is still the initial amount, r is the rate of decay in decimal form, and t is time. Notice that a is greater than 0 again, but r is between 0 and 1. So it's a... and whereas for our r in exponential growth functions, r is greater than 0. So for exponential growth, the value inside the parentheses is greater than 1 because r is added to 1. For exponential decay, the value inside the parentheses is less than 1 because r is subtracted from 1. So we'll use this idea later on to determine which functions are growth or decay, and eventually writing functions. So we're going to determine whether the table represents exponential growth or exponential decay, or neither. So the first thing that we need to check for, and again, pause as you need to so that you can copy this down and follow along. The first thing that we need to check is that x is increasing by the same amount, which it is. So I'm going to write that down. That's always important to check. Sometimes we forget to do that. And we need to determine the pattern in the y. So as x is increasing by 1, it looks like you could think of this as dividing by, it looks like 3. So remember, dividing by 3 is the same thing as multiplying by 1/2. So I want us to actually write this down as multiplying by, or not 1/2, 1/3. We're multiplying by 1/3. So the reason why is because we need to determine, eventually we will need to know what r is if we're decreasing, and in this case r is 1/3. So always express these values as multiplication. So if we're dividing by 3, again, that's the same thing as multiplying by 1/3. So we're multiplying by 1/3, multiplying by 1/3. So if we are decreasing, then this is going to be decay. This is exponential decay because as x increases by 1, y is multiplied by 1/3, which means that it decreases. Okay. And for b, we're increasing by 1. And we are multiplying by 2. And our y values are increasing. So this is going to be exponential growth. And because as x increases by 1, y is multiplied by 2. And it is increasing. Interpreting exponential functions, so this is example 3. Determine whether each function represents exponential growth or decay. Identify the percent rate of change. So if the number inside, remember we mentioned before, if the number inside the parentheses is greater than 1, then that means that it's growth. So this is exponential growth. Identify the percent rate of change. Well, in the formula, this is 1 plus r. 107 is. So to find r, we can set that equal to 1 plus r and solve for r. So subtract 1, and r is equal to 0.07. So that is our decimal value for r, and that means that the percent rate of change, I'm going to convert that to a percent. We have a growth rate of 7%. That's called our growth rate. Okay. Now it's always the number inside the parentheses. So some of you might be looking at this 0.2 and saying, well, maybe that is decay. But it is decay, but not because that's 0.2. It's because of the number inside the parentheses. If it's less than 1, then we are dealing with an exponential decay function. So that means that as t increases by 1, our overall or our total value is decreasing. So again, that's 1 minus r. This is going to be decay. And again, it's simply because this value is less than 1. And we can set it equal to 1 minus r. Solve for r, so subtract 1, and we get negative r is equal to negative 0.02. So divide both sides by r, and r should be 0.02. Remember that r should always be a positive value because ultimately you subtract r from 1, and when it's decay, r is between 0 and 1. It's a decimal value. So r is, not r, the decay rate is 2%. Is 2%. Okay. And we'll stop there, I believe. Yeah, we'll stop there, and you'll have an assignment over. Oh, I'm sorry, I lied. I do want to get through example 4. My bad. So let's do example 4, and then we'll be done. So we're going to rewrite each function to determine whether it represents exponential growth or exponential decay. So notice that the functions that we were given before, if I scroll up, t is by itself. T is its own exponent. So they're basically wanting us to rewrite these functions so that we can determine if it's an exponential growth or decay function. So this is where our properties of exponents are going to come in. So this might be, for the most part, you might have seen most of the, everything that we've talked about so far. You may have seen this last year. This might be new. So we're going to start by, we have to do some kind of tricky exponent rules. So we want t to be kind of alone. So we're going to start by rewriting this as we're going to separate t out from the fraction t over 4, okay? And so it's like we're factoring it out. What's left is 1/4. Now that might be a little bit confusing. So remember that a power of a power rule, I'm essentially applying that in reverse. So a power of a power rule, let's say I was given this initially and I said, well, let's multiply those exponents. That would be t times 1/4 or t over 4. So I'm essentially using a power of a power rule in reverse. The power of a power rule says that, well, if I have a to the mn, I can make that a to the mn. Well, what I've done here instead is I've started with this and I've turned it into that. So again, if this is a little tricky for you, we'll definitely talk about it when I come back. So the reason why we want to do this is because we can actually evaluate 0.96 to the 1/4 power. Type that into your calculator and you get 0.99. Okay. So now that it is in the proper form, y equals, we have our initial value, we have our this is our 1 minus r. We could, since it's less than 1, it's decay, and it's raised to the t power. Since it's in the proper form, we can determine that this is a decay function. And it's because this value inside the parentheses, which I'm going to highlight, is less than 1. Okay. Let's look at B. Applying the properties of exponents. So remember, when we subtract exponents, that means that we have the same base, but it was 1.1 to the t over 1.1 to the third, because we can subtract those exponents. So again, I'm applying this rule. We've done problems like this where we've started with this and come up with this. But what we're essentially doing now is we're working in reverse. We're starting with this, and we actually need to go to that. Okay. So 1.1 to the t over 1.1 to the 3. And I can do that because this is the same base, and my exponent rule, my subtraction rule, says that I subtract my exponents. Okay. So I can evaluate 1.1 to the third. Okay, 1.1 to the third is actually about 0.75. Okay, 1.1 to the third, if you type that into your calculator, it gives you about 0.75. And you still have the 1.1 to the t. Okay, so this is equal to this 0.75. So f of t is equal to 0.75, 1.1 to the t. So this is exponential growth. And it's because this value inside the parentheses is greater than 1. Now, going through this example, I have a feeling that a few of you might struggle with a couple problems like this. That's fine. Just try them out. I'm going to give you problems like the other examples too, examples 1, 2, and 3, and I'll go over any questions that you have next time. Thanks, guys.